This is exercise 36 in section 11.5, which is on page 787 if you want to follow along in the textbook. The radius of a right circular cone is increasing at a rate of 1.8 inches per second, while its height is decreasing at a rate of 2.5 inches per second. At what rate is the volume of the cone changing when the radius is 120 inches and the height is 140 inches? So first of all, this type of question should be familiar to you. You did ones very similar to these back in chapter 4 when you took calculus 1. It's a related rates question, but this time we will use the chain rule to answer the question. So first of all, let's draw a picture of this. So we have our cone. I'll just draw a basic cone. So we have the height of the cone is 140 inches right there, h. So h equals 140 inches. And it says the height is decreasing at a rate of 2.5 inches per second. So that means that dh dt, so this is an ordinary derivative, it's not a partial derivative. Dh dt is negative 2.5 inches per second. Okay, now we also have radius. Here, I'll switch colors for the radius here. So radius, it says the radius is right here, 120 inches. And then dr dt, the rate of change of the radius with respect to time is, it says it's increasing at a rate of 1.8 inches per second. 1.8 inches per second. Okay, now we also have the volume of a cone. This is one of those things. If this comes up on a test, I'll just give you the formula for it. For homework, whenever there's a geometric question like this, you can look up the formula. There's the reference page in your textbook. You can also Google it to get it. But anyways, the volume of a cone is 1/3 pi r squared h. All right, now this is a function of two variables, which makes this a chapter 11 question. You could say, we have the independent variable r, independent variable h, and both of them are being used to compute the radius. So I forgot to draw a little line for the radius right there. Now you can solve this using chapter 4 methods, but it's actually easier, especially when you have a function of two variables. It's easier to solve this using chapter 11 methods, the multivariable stuff. All right, so first of all, with all the chain rule questions, it really helps to make that little tree diagram. So we have volume is a function of radius and height. And it's totally fine just to keep the function in terms of two variables. Often, if you remember with those related rates questions, and by the way, those optimization questions, you often had to cleverly rewrite your function in terms of just one variable, like you're also told like the height is twice as long as the radius or something. But on this one, we have a lot more flexibility with the tools to work with two variables. So anyway, volume is a function of rate and height, radius and height, and then radius is a function of time, only time. If you wanted to, you could actually write the function. We don't have to, but you could say that radius is 1.8 times t right there. But I'll just put that in parentheses. You don't really have to write that out, but it's just, that's what the function is. And then height is also a function of time as well. All right, well, I guess 1.8 t plus some initial value. But again, I don't really care about that function. I just need to know that it's a function of time. Okay, so like the other chain rule questions, at this point you can write up your derivatives, and so we have dv dr. So this is a partial derivative because it's a function of two variables. So dv dr, we have dh dr, excuse me, I'm sorry, dv dh, and that's a partial derivative as well. And then r is a function of time, so we have dr dt, an ordinary derivative, and dh dt. Okay, so at this point, we can write out our chain rule equation. And in the textbook, the chain rule equations, they look super confusing, but all you need is a tree diagram, and it tells you exactly how to set it up. So you just follow every branch of this tree. And so we have dv, right? So dv dt, which is an ordinary derivative because volume is a function of one variable t, is equal to the partial derivative dv dr times dr dt. Oh, dr dt, that's a regular derivative right there. We have the partial derivative dv dr, and then and that's the first branch of the tree, and then plus, you just add up all the branches together, and so then plus dv dh, that's a partial derivative right there, times the ordinary derivative dh dt. If you get confused about when to use partial derivative and when not, if you have a derivative of one variable, then it's a regular derivative, or if a function of one variable. If you have a function of more than one variable, then you have to do the partial derivative. And so there's the ideas. Now, the logic in this particular context, we have, you can see the dr's will cancel, and so you have dv dt, which is, the units would be cubic inches per second, and over here in the second term, the dh's will cancel, and so you have, again, cubic inches per second. And so we have the overall volume is cubic inches per second plus, excuse me, cubic inches per second equals cubic inches per second plus cubic inches per second. All right, so now we just start working it out. And so dv dr, all right, so now it's back to our formula right here, the formula for volume. So let's do the partial derivatives. Let me erase the tree diagram. I don't need the tree diagram anymore, but I do need some space to work out my partial derivatives here. So I've got dv dr. So r is the variable, h is the constant. Actually, let's rewrite this as in this way. So 1/3 pi h is all just a constant times r squared, was the r is the variable. So then just power rule, move the 2 down in front. So we have 2/3 pi h times r. Okay, and that's it for the partial derivative with respect to r. Now we can go ahead and plug in h and r right now and get the actual rate. And so it says here in the original question, h is 140, r is 120. So that will be 2/3 times pi times 140 times 120. Okay, 3 divides into 120 40 times. So I've got 2 times 140 times 4. I did this already to save a little time. It's 11,200 pi. And that would be cubic inches of volume per inch of radius. So in other words, at this moment in time when the radius is 120 and the height is 140, if the radius grows by 1 inch, the overall volume will increase by 11,200 pi cubic inches, which is like 30,000 something cubic inches. So this is a very quickly increasing volume here. Now so anyway, that's dv/dr. Let's go ahead and plug that in right here. dv/dr is 11,200 pi. Okay, now dr dt, that's just given. dr dt is 1.8. So I'll just multiply that right now. Okay, now the units, let's include the units here, because the units, especially with these related rate questions, it really helps to have the units. So this is cubic inches per volume per inch of radius times 1.8 inches of radius per second. And so you can see the inches will cancel, and you have cubic inches per second. All right, and we'll compute that later, but for now I'll just leave it in there. Okay, now let's go to dVdh, the partial derivative dVdh. So back to this this function right here. Let me erase this so I can show you in that same little spot because I'm running out of space otherwise. Let's erase this too. So now I will take the partial derivative of volume with respect to h. So now h is the variable. 1/3 pi r squared is all just a constant. And so I've got a constant times h. So dVdh is just 1/3 pi r squared. It's just a constant times h. So the derivative of h is 1, and then times the constant. All right, so interesting that h is not a player in this. In essence, h volume is increasing, or in this case, decreasing linearly. So the derivative is constantly changing in a linear fashion with respect to h. So now r, where's r? R is r is 120. So plug in 120. I've got 1/3 times pi times 120 squared. Okay, I worked this one out in advance just to save a little time. So it's 4,800 pi, and this is cubic inches of volume per inch of height. Okay, so now back to our chain rule formula. So dVh dt I just figured out is 4,800 pi cubic inches of volume per inch of height times the rate of change, dH dt, negative 2.5 inches of height per second. So again, you can see the inches will cancel, and you'll have cubic inches per second. And so dV dt, cubic inches per second, is equal to, you can see, cubic inches per second plus cubic inches per second. So at this point, inches cancel there, inches cancel. Everything is now cubic inches per second, and just add these together. Well, actually, this is the negative. I got negative 2.5 times 4,800 pi. I'll let you do the arithmetic on your own, and it turns out to be 8,160 pi. So it's positive because the increase in volume as a function of radius the volume is increasing faster over here than it's decreasing because of the shrinking height over there. And then the units would be cubic inches per second. So there's the answer right there. Now, I'd like to also show real quick on Mathematica. You can use the graphics 3D cone command here. Just a quick little picture showing. You can see that the height is decreasing, and then the radius is increasing. And so the overall volume, it doesn't look like it from the picture, but actually the overall volume is increasing a bit. And then one more thing, this is a nice way to check your work. I have the volume as a function of r and h, 1/3 pi r squared h. Here, let me zoom this in a little bit here. Okay, and so I set up my volume. The volume when r is 120, h is 140, is 2.1 times 10 to the 6, about 2 million cubic inches altogether. And what you can do is ask yourself, okay, well, 1 second ago, what was the radius and height? 1 second in the future, what would be the radius and height? So 120 plus 1.8, 140 minus 2.5 was, that's 1 second in the future, minus 1 second in the past. Subtract them, divide by 2, and you get an average rate of change over a 2-second time period, which is about 25,000 cubic inches per second. And then I took my actual answer, 8,160 times pi. I got, again, roughly 25,000 cubic inches per second. So because those numbers are so closely